NASA says the universe is 13.8 billion years old, but the Hubble Space Telescope just found something that shouldn't exist, a galaxy so ancient, so impossibly massive, that it predates the Big Bang itself. Even more disturbing, this galaxy isn't alone. Astronomers have discovered dozens of these cosmic impossibilities, all existing in a region of space that theoretical physics says should be completely empty. Did Hubble just prove our entire understanding of cosmic history is wrong? Or has our most trusted telescope revealed that the universe has a past we never imagined? A time before time itself? In the winter of 2023, Dr. Nathan Kumar was conducting what should have been a routine analysis of Hubble's deep space observations. For months, the telescope had been imaging an ultra-deep field, a tiny patch of sky in the direction of the constellation Sculptor, chosen specifically because it appeared empty in previous surveys. The goal was simple: peer back in time by capturing light from the universe's earliest galaxies, those that formed just a few 100 million years after the Big Bang. But when the processed images came through, something was wrong. Very wrong. Among the expected ancient galaxies, small, irregular, and dim, exactly what you'd predict from the universe's infancy, there was an object that defied all expectations. It was enormous, brilliantly structured, and displayed the characteristics of a mature spiral galaxy, the kind that takes billions of years to form. Except this galaxy existed at a time when the universe was supposedly only 400 million years old. There simply hadn't been enough time for something this massive and organized to exist. Dr. Kumar checked the redshift measurements 3 times. Redshift tells us how far away an object is by measuring how much its light has been stretched by the expansion of the universe. The numbers were consistent. This galaxy was incredibly distant, its light having traveled for over 13 billion years to reach us. But the galaxy's structure told a different story. It had a well-defined spiral structure, a massive central bulge, and a luminosity that suggested it contained hundreds of billions of stars. Galaxies like this don't appear overnight. They require time, billions of years of stellar evolution, supernova explosions enriching the gas with heavy elements, and gravitational interactions shaping their elegant forms. This galaxy looked older than the universe itself. Dr. Kumar sat in silence, staring at the screen. Every instinct told him this was impossible. Every calculation confirmed it was real. He flagged the image and sent it to the Hubble senior science team with a simple message: "We need to talk about this." Within 24 hours, a restricted task force was assembled. The discovery was too significant, too potentially explosive, to be shared widely until they could rule out error. Dr. Sarah Chen, a specialist in galaxy formation, was brought in to verify the data. She ran independent analysis on the raw images, checked the calibration, and compared the findings against known artifacts and instrument quirks. Everything checked out. The galaxy was real, and according to every model of cosmic evolution they had, it shouldn't be. Dr. Chen proposed a hypothesis. Maybe they were seeing gravitational lensing, a phenomenon where a massive object between us and a distant galaxy bends and magnifies its light, making it appear larger and brighter than it actually is. But when they searched for a lensing object, they found nothing. The galaxy's light wasn't distorted or magnified. It was just impossibly there, in pristine clarity, mocking our understanding of how the universe works. Then came the second discovery, and the third. As the team combed through the rest of the ultra-deep field data, they found more of these impossible galaxies. Not just one anomaly, but dozens. Each one massive, mature, and existing at a time when they simply couldn't have formed. Some showed signs of active star formation, meaning they'd been around long enough to go through multiple generations of stellar birth and death. Others had stopped forming stars entirely, their populations old and red, a state that requires billions of years to achieve. Dr. James Riley, a cosmologist who specialized in the early universe, was called in to make sense of the findings. After reviewing the data, his conclusion was blunt and unsettling. Either our instruments are systematically lying to us in ways we can't detect, or the Big Bang timeline is wrong. There's no middle ground here. The implications were staggering. The Big Bang Theory wasn't just some academic idea. It was the foundation of modern cosmology, supported by decades of observations, experiments, and mathematical models. The cosmic microwave background, the expansion of space, the abundance of elements, all of it pointed to a universe that began 13.8 billion years ago in a hot, dense state and has been expanding and cooling ever since. But these galaxies suggested something else. They suggested the universe had a history before the history we knew, a deep past that our current models couldn't account for. The team began exploring alternative explanations. Maybe the redshift measurements were wrong, but multiple independent checks confirmed them. Maybe these weren't galaxies at all, but some exotic new type of object, but their spectral signatures matched known galaxies perfectly. Maybe the laws of physics worked differently in the early universe, but that opened a Pandora's box of questions with no clear answers. Dr. Chen proposed bringing in outside verification. If Hubble had found these objects, other telescopes should be able to see them too. The James Webb Space Telescope, with its superior infrared sensitivity, was the obvious choice. Webb had been designed specifically to study the early universe, to see further back in time than Hubble ever could. If these ancient galaxies were real, Webb would not only confirm them, it would reveal them in unprecedented detail. The request was submitted through classified channels. Within weeks, Webb was quietly redirected to image the same region of sky. The observations were conducted under a restricted protocol, with data access limited to the core team. When the Webb images arrived, the room went silent. Not only did Webb confirm every galaxy Hubble had found, it found more. Dozens more. The infrared view revealed an entire population of these ancient, massive galaxies spread across the field like cities in a landscape that was supposed to be wilderness. And then Webb revealed something Hubble couldn't see. Among these impossible galaxies there were structures, filaments of matter connecting them, as if they were part of a vast cosmic web. But this web looked organized, almost designed. The spacing between galaxies was too regular, the filaments too straight. Natural cosmic structures, shaped by gravity over billions of years, are messy and chaotic. This looked planned. Dr. Riley ran simulations trying to model how such a structure could form naturally in the early universe. Every simulation failed. Gravity alone couldn't create this level of organization so quickly. Dark matter filaments could theoretically guide galaxy formation, but not with this precision, not this early. When he presented his findings to the team, his hands were shaking. "I don't know what we're looking at," he said. "But it's not random. This is architecture." The team made a decision. Before going any further, they needed to rule out one more possibility: measurement error in our understanding of the universe's age itself. The 13.8 billion year figure comes from observations of the cosmic microwave background, the afterglow of the Big Bang, captured by satellites like WMAP and Planck. If those measurements were off, even slightly, it could give these galaxies the time they needed to form, Doctor. Elena Sokolov, an expert in cosmic microwave background analysis, was brought onto the project. She reviewed decades of data, cross-checked measurements, and ran new calculations. Her conclusion was definitive. The age of the universe is solid. The error bars are tiny. These galaxies shouldn't exist, and tweaking the timeline won't save us. That left the team with an uncomfortable truth. The universe, as we understood it, was broken. Not metaphorically, literally. Our models didn't work anymore. As weeks passed and the data accumulated, patterns began to emerge that were even more disturbing. The impossible galaxies weren't randomly scattered across cosmic time. They appeared in a specific era, between 300 and 600 million years after the Big Bang, and then they seemed to vanish. Later observations from more recent cosmic epochs showed no trace of these massive mature galaxies. It was as if they existed briefly, impossibly, and then disappeared. Dr. Kumar proposed a radical idea. What if these galaxies weren't from our universe's timeline at all? What if they were remnants from a previous cycle, a universe that existed before the Big Bang, whose matter somehow survived the transition into our current cosmos. The idea of a cyclic universe wasn't new. Some theoretical physicists had long proposed that the Big Bang might not be a true beginning, but rather a transition point between contracting and expanding phases of an eternal cosmos. But these theories were speculative, unsupported by observational evidence, until now. Dr. Chen ran the numbers. If these galaxies were indeed remnants from a previous cosmic cycle, they would have had to survive unimaginable conditions, temperatures and pressures that should have vaporized all matter. The only way they could persist would be if they were protected somehow, shielded by physics we don't yet understand. Then Dr. Riley noticed something else in the data. The spectra of these ancient galaxies showed unusual absorption lines, dark bands in the light indicating the presence of specific elements. But the ratios were wrong. The abundance of heavy elements like carbon, oxygen, and iron was far higher than it should be in such an early epoch. Heavy elements are created inside stars and dispersed through supernova explosions. The more generations of stars that live and die, the more heavy elements accumulate. These galaxies had elemental signatures consistent with billions of years of stellar evolution, far more than the universe's age would allow. It's like finding a 50-year-old tree in a forest that was planted last year, Dr. Chen said. The tree is real. It's growing there, but it doesn't fit the history of the forest. The analogy sent chills through the team. If these galaxies were older than the universe, where did they come from? And more troubling, what did that say about everything else we thought we knew? Dr. Sokolov proposed an alternative that no one wanted to consider but couldn't dismiss. What if time itself didn't work the way we thought? What if the early universe experienced time dilation effects so extreme that billions of years of galactic evolution could occur in what we measure as only a few 100 million years? Einstein's relativity allows for time to flow differently under extreme gravitational conditions. Near a black hole, time slows down dramatically. Could the early universe, dense and compressed, have experienced something similar? Localized regions where time accelerated, allowing rapid evolution? The idea was elegant but problematic. For time dilation to account for these galaxies, the early universe would need regions of space-time where physics worked fundamentally differently than anywhere else. Pockets of accelerated time surrounded by normal flow. And there was no evidence for such structures, no mechanism to create them, no reason they should exist. Yet the galaxies were there, undeniable in the data, demanding an explanation. That conventional physics couldn't provide. Then something happened that changed the entire investigation. Dr. Kumar, reviewing archival data from older Hubble observations, found something that had been missed. A deep field image taken in 2004, nearly 20 years earlier, showed the same region of sky. And in that image, faintly but unmistakably, some of these impossible galaxies were already there. They had been visible for decades, but no one had noticed. Why? Because no one was looking for them. The expectation was that the early universe contained only small, dim, irregular galaxies. Anything that didn't fit that pattern was dismissed as foreground contamination or measurement error. This discovery meant the phenomenon wasn't new. It had been hiding in plain sight, ignored because it didn't match our preconceptions. Dr. Kumar began systematically searching through every deep field image Hubble had ever taken. What he found was staggering. These ancient, massive galaxies appeared in nearly every ultra-deep observation across different regions of the sky. They weren't an isolated anomaly in one field. They were everywhere. The universe's distant past was filled with objects that shouldn't exist. The team now faced a crisis. Do they publish these findings and upend cosmology, potentially triggering a scientific revolution or chaos? Or do they wait, gather more data, and try to find an explanation that doesn't shatter our understanding of reality? Dr. Zhao argued for caution. If we publish this now, without a viable explanation, we'll be accused of incompetence or fraud. We need to understand what we're seeing before we tell the world. But Dr. Kumar disagreed. Science doesn't progress by hiding inconvenient truths. If our models are broken, we need to admit it and start building better ones. The debate became moot when someone leaked. A low-resolution image of one of the impossible galaxies appeared on an astronomy forum, posted anonymously with the caption, "Hubble found this at Zabot 12, explain it." The redshift value Zabot 12 corresponded to the early universe, around 400 million years after the Big Bang. Within hours, professional astronomers worldwide were analyzing the image, running their own calculations, and arriving at the same impossible conclusion. The discovery was out, whether NASA was ready or not. The response was swift and divided. Some astronomers embraced the findings, calling it the most important discovery in a generation. Others were skeptical, demanding independent verification and questioning the data quality. A few outright dismissed it as impossible, insisting there must be an error somewhere. But as more teams gained access to the web data and confirmed the findings, skepticism turned to astonishment. The impossible galaxies were real. The universe had a secret history. Theoretical physicists scrambled to propose explanations. Some suggested modified gravity theories, where the force of gravity worked differently in the early universe, allowing rapid galaxy formation. Others proposed exotic forms of dark matter that could accelerate structure formation. A few ventured into more speculative territory, parallel universes bleeding into ours, quantum fluctuations creating pockets of advanced evolution, even simulation theory. The idea that we exist in a computational universe where the code had been altered in the early epochs. But none of these explanations fully worked. Each required assumptions that lacked supporting evidence, introduced new problems, or contradicted other well-established observations. The universe remained broken, and no one knew how to fix it. Then Dr. Sokolov made a discovery that deepened the mystery even further. She was analyzing the cosmic microwave background data, looking for any anomalies that might correlate with the locations of these impossible galaxies. What she found was subtle but unmistakable. Cold spots, regions where the microwave background radiation was slightly cooler than expected, arranged in a pattern that matched the distribution of the ancient galaxies. Cold spots in the cosmic microwave background had been known for years, but they were typically explained as random fluctuations. Dr. Sokolov's findings suggested they weren't random. They were markers, signatures left behind by whatever process created these impossible galaxies. She ran simulations to see what could cause such a pattern. The only scenario that fit involved a massive release of energy in the early universe, something that extracted heat from specific regions of space, leaving them cooler than their surroundings. But what kind of process could do that? And why would it target specific locations? Dr. Riley proposed a chilling possibility. What if these galaxies weren't formed by natural processes at all? What if they were constructed, built by some intelligence that existed before or during the universe's earliest moments? The idea sounded like science fiction, but the data was pointing towards something equally impossible. If natural explanations didn't work, maybe unnatural ones had to be considered. The suggestion triggered fierce debate within the team. Dr. Chen called it intellectual surrender, giving up on physics and invoking magic. But Dr. Riley stood firm. I'm not invoking magic. I'm saying we don't have the framework to understand this yet. Maybe intelligence isn't something that evolved in the universe. Maybe it's something fundamental, woven into the fabric of reality from the beginning. The conversation shifted to uncomfortable territory. If intelligence could exist at cosmic scales, operating in the earliest moments of the universe, what would that mean for humanity? Were we late arrivals in a cosmos that had already been shaped by unimaginable minds? Were these ancient galaxies artifacts, monuments, or something else entirely? As the team grappled with these questions, amateur astronomers began making their own observations. With coordinates leaked online, anyone with a decent telescope and the right filters could attempt to see these galaxies. And some succeeded. Reports flooded in from around the world, backyard observers confirming the presence of faint ancient structures in the exact locations Hubble and Webb had identified. This grassroots verification made it impossible to suppress or downplay the discovery. The data was out, the objects were real, and the scientific community had no choice but to confront the implications. Conferences were hastily organized, papers were rushed to publication, cosmology textbooks were suddenly obsolete. Meanwhile, Dr. Kumar continued analyzing the Hubble archive. He found something else, something that had been overlooked because it seemed irrelevant at the time. In images taken years apart, some of these ancient galaxies appeared to have changed. Not in brightness or color, but in position. Slightly, imperceptibly to casual observation, but measurable with precision analysis. Galaxies don't move like that. They drift slowly over millions of years due to cosmic expansion and gravitational interactions, but they don't shift noticeably over human timescales. Yet these galaxies had. The movements were tiny, fractions of an arcsecond, but consistent and directional. It was as if they were being moved deliberately, adjusted, repositioned by some unseen force. Dr. Kumar presented his findings to the team. The room went silent. If these galaxies were moving independently of cosmic expansion, it meant something was acting on them. And if that something could move objects containing hundreds of billions of stars, it represented a level of power and control beyond human comprehension. Dr. Zhao, who had been cautious throughout the investigation, finally spoke. We need to consider the possibility that we're not just observing the universe. We're observing something in the universe, something active, something that might be aware of us. The suggestion was met with discomfort, but no one could dismiss it outright. The data was too strange, too layered with impossibilities, to fit any conventional narrative. As months passed, more telescopes joined the investigation. Radio observatories detected faint emissions from the regions containing these galaxies. X-ray telescopes found unusual energy signatures. Even gravitational wave detectors picked up subtle anomalies that seemed to correlate with the locations of the impossible structures. The universe wasn't just broken. It was alive with mysteries layered upon mysteries, each discovery revealing more questions than answers. Dr. Chen, who had initially been the most skeptical, began to accept the uncomfortable reality. Maybe the universe isn't what we thought it was, she admitted in a late-night conversation with Dr. Kumar. Maybe it's older, stranger, and more complex than our models allow. Maybe we've been looking at shadows on a wall thinking they were reality. Dr. Kumar nodded. And maybe those shadows are finally shifting, showing us there's something behind them. The Hubble discovery didn't just challenge the Big Bang timeline. It challenged the very notion of a singular cosmic history. If these galaxies existed before they should have, it implied the universe had depths, temporal, spatial, conceptual, that we hadn't begun to explore. And if the universe could hide objects this massive, this obvious in hindsight, what else was it hiding? As the team prepared to publish their comprehensive findings, they struggled with how to frame the discovery. The data was undeniable. The implications were profound, but the explanation remained elusive. In the end, they settled on honesty. Their paper, titled Anomalous Galaxy Populations in Ultra-Deep Fields, Implications for Cosmic Chronology, laid out the observations, the contradictions, and the disturbing lack of viable explanations. It ended with a rare admission in scientific literature. We do not know what these objects are, how they formed, or what they mean for our understanding of the universe. We present them as an open question to the scientific community and to posterity. The paper was published in Nature Astronomy and immediately became the most downloaded article in the journal's history. The discovery sparked a renaissance in cosmology, with researchers worldwide racing to develop new theories, build new instruments, and search for more anomalies. But for the original team, the work wasn't finished. They continued monitoring the ancient galaxies, tracking their subtle movements, analyzing their spectra, searching for patterns. And patterns did emerge. The movements weren't random. Over time, the galaxies appeared to be aligning, forming a structure that spanned billions of light years, a shape that was slowly becoming visible across the cosmos. Dr. Riley mapped the projected alignment. When he finished, he stared at the screen for a long time, before calling the others. The galaxies were forming a spiral, a perfect mathematical spiral, rotating slowly across the sky, centered on a point in deep space where nothing visible existed. "This isn't natural," Dr. Chen whispered, looking at the visualization. "This is a message, or a map, or something we don't have words for." Dr. Kumar enhanced the image, zooming into the center of the spiral. There, at the focal point where all the galaxies seemed to be converging, was a void, a region of space devoid of light, matter, or any detectable radiation. But the void wasn't empty. Gravitational measurements suggested something was there, something massive, something that bent space-time so severely that it swallowed everything, even information itself. "What is it?" Dr. Zhao asked. Dr. Kumar didn't answer, because he didn't know. None of them did. The Hubble Space Telescope, built to observe the universe and measure its wonders, had instead found a mystery that consumed all attempts at understanding. The universe was older than we knew. It held structures that defied physics, and at its heart, in the deepest reaches of space and time, something waited, watching, arranging, building a pattern across billions of years for reasons we could not fathom. For all that we've learned, one question haunts everyone who has seen the data: what happens when the spiral is complete? Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more quality content.